All right, thank you. Our next speaker is Nathaniel Robinson. He's a research scientist at the University of Montana based in Missoula, where his work focuses on developing remote sensing-based data sets and products to monitor rangeland productivity across broad spatial temporal scales. Please help me welcome Nathaniel.
I'm going to talk this morning about our production models that we've built off of some already existing underlying models of productivity and production, and how we're optimizing those specifically for western rangelands in North America. So before I begin, I really want to define what productivity is, because it can be thought about in a number of different ways. And as in a rangeland meeting, there's probably some very strong opinions on what those ways are. So I'll be clear as to how I'm talking about it. In its broad sort of sense, production is defined as the conversion of solar energy to chemical energy through the process of photosynthesis, and it's often represented as some sort of biomass or carbon quantity. Productivity is the rate of that production, or how quickly that production is happening over a given space and over a given time. Ecologists like to define or think of it as gross primary production and net primary production. And these are essentially very similar things. Gross primary production is how much carbon is taken out from the atmosphere and into plant matter, while net primary production is that minus what's lost due to respiration. So that's what we think about and what our models are built off of. Most managers, rangeland people, they like to think of things as biomass, standing crop, and it's much more applicable to on the ground, how much forage is available for your wildlife or livestock. And what's great is when you start with these things are foundational for these. So starting with GPP, gross primary production, and net primary production, we can do some gymnastics and get to biomass, above ground biomass, and that kind of thing, and eventually forage for livestock and wildlife, and that's where we're headed. So all of these things are built off of what we have spent the past 2 to 3 years building, is this GPP NPP product for the continental United States. And like Brady said, this is built off of the Mod 17 net primary productivity model, which is at 1 kilometer or 500 meter resolution. When I say resolution, that's the pixel size, so 500 meters by 500 meters. And for rangelands, you know, at a broad scale, you can look at, you know, big trends through time. But when you think of 500 meters on the ground, how much is happening within that 500 meters? A lot. And so scaling that down to 30 meter spatial resolution was a huge step forward. And when you think of 30 meters by 30 meters, that's about the size of a baseball diamond, similar to the size of this room probably, maybe a bit bigger. And for rangelands, that's still not detailed enough. There's still a lot of heterogeneity within that plot, especially when you're looking at allotment scales or ranch scales and trying to monitor your productivity at those scales. There's a lot going on. So our goal was to continue to refine that. And the other big advancement was the time scale of these products, 1984 to 2018. The current existing products before this only went back to around 2000, 2001. So we extended that time scale substantially. So what does that product give us? Well, it gives us GPP and NPP. That's kilograms of carbon per meter square. And the GPP product is every 16 days, so kilograms carbon per meter square for every 16 days. And the NPP product is annual, so one sort of estimate every year. And it gives us total plant carbon, so below and above ground carbon. And we can sort of split that up into grasses and shrublands based on the NLCD, National Land Cover Data Set. So at 30 meters, we could say this grassland plot gives us, you know, X amount of carbon per meter square per 16 days or per year. But that's, like I said, not good enough. One, because there's a lot going on below that 30 meters. And for rangelands, you know, grasses is a complicated cover type. We want to look at annuals and perennials and shrubs, these sort of functional groups. And we want to go from NPP, this full plant carbon, to above ground biomass, which is pounds per acre or kilograms per hectare, depending on where you are in the world. And so that was our goal. Can we take this existing NPP product and GPP product and refine it to these sub-pixel plant functional groups? And luckily, we can. Because when you think about it, if you look at a Landsat pixel up there on the left, 30 meters by 30 meters, and just so you know, the NPP, GPP products, the foundation of them from the remote sensing side is the NDVI, the Normalized Difference Vegetation Index. And so that's essentially a measure of greenness that you can get from satellite data. And if you look at a profile through time, sort of, for a pixel, you get a single pixel, and it has this nice flow, and vegetation grows up in the spring and summer, and then dries out in the fall, and it's non-existent in the winter, pretty much. But that's not reality. If you go below a 30-meter pixel, you have these plant functional groups that make up that pixel, and not even this cleanly. It's probably more sort of mixed up in there. But you have bare ground, a component of bare ground. You have a component of annuals, a component of perennials, a component of shrubs. You could add trees in there. You can add litter in there. It gets pretty complicated. But we focus on these ones. And each of these, based on their fractional cover and their individual phenologies, drive a component of that pixel profile. So, like I said, that pixel NDVI on the bottom left is a function of both the amount of each of those plant functional groups that's in that pixel, plus what's happening at any given time. So we can take that idea, have our underlying NPP, GPP model, plus the new fractional cover data set developed by Matt Jones and Allred and others, and combine those two through space and time, and sort of solve the equations for what each plant functional type is doing. And this is how we do it. If you think about it, each of those profiles are doing a different thing through time and contributing to the overall profile. And we have the total pixel NDVI and the fractional cover of each component. But we don't know that. But because we have the variability across space, we can build an overdetermined set of equations and use ordinary least squares to sort of solve for, what value of NDVI for each of those land cover types minimizes the error. And that's what we were able to do using Earth Engine, using Matt's product through time, the fractional cover, and using our underlying NDVI data set that was used to build the NPP and GPP products. And once we have those NDVI profiles for each land cover type, we can plug those back in to the NPP and GPP model and come up with estimates for NPP and GPP for each of those plant functional groups for each 30-meter pixel from 1984 to 2018. So just to give you an example of how this works, if we look at 2 points, one in central Montana and one in southern Arizona, two points with very different phenological characteristics, and we build these underlying NDVI profiles, if that's the pixel level profile for each of them, makes sense. Montana is largely spring, winter precipitation driven, and southern Arizona is largely driven by these late summer, early fall monsoons. The NDVI profiles look something like that. And we start partitioning it out. You have your annuals that look like this, bump up real fast in both cases. And the percentage next to the AFG there that's the fractional cover within the pixel. So in Montana, the fractional cover of annuals 7%. In Arizona, the fractional cover of annuals was 15%. And perennials is what you'd expect to some degree. You get a little bit more sustained productivity, through the season. Oh, sorry. Shrubs, again, what you'd expect, sort of this low but stable NDVI through the season. And then, bare ground, the component of bare ground, I didn't put that in there, but that would stay stable along close to zero. And then when you plug that back in to the GPP and NPP algorithm, which also now takes into account the contribution due to their fractional cover, you get GPP through a year that looks like this for each of those points. And again, in both cases, you can see that the perennial productivity is largely what drives the productivity of these systems. The annuals, despite there being substantial NDVI, or even substantial percentage of 15%, it really doesn't contribute hardly at all to the overall productivity of the system. Then if we take the GPP product and plug it into NPP, again, you can see that it's the perennials that really drive the productivity of these systems. Where perennials are 61% of the fractional cover in the Montana, they're upwards of 90% of the production. And in Arizona, 47% to 80%. Just it gives you some interesting takes on what's going on in these systems. Now those were individual pixels, we can also map this across space. So this is for 2017 for Montana, where we can get, and converted now to above ground biomass just through some basic conversion factors. And we can look at above ground biomass in pounds per acre for perennials, annuals, and shrubs. And again, you can see that it's really perennials that are driving overall productivity of these areas. But you can start seeing interesting trends of annual productivity increasing or decreasing and shrub productivity increasing or decreasing. And we can zoom in and we can sort of aggregate at different scales. And that's what I did next, is looking at a specific location, the Soda Fire, which burned in 2015 just south of Boise, which is a place we went on a field trip at last year. And looking at individual BLM allotments within the Soda Fire through the last 10 years. And when you plot perennials, you look at how the drought affected perennial productivity and how they recovered post-drought, and then how fire affected perennial productivity. And again, there was a lot of treatments in this area post-fire, so we can then look at BLM allotments and treatments. And if you throw in annuals on top of that, you can again see how the drought really didn't affect annual productivity that much, but it was that increase in annual productivity before and after the fire that maybe was a big component in how that fire acted in that area, which goes along with a lot what of the research is showing on how that fire spread and the effects of that fire. And then shrubs, again, as you'd expect, sort of stable and low through time. So that's where we're at with the optimized productivity. Again, taking complete plant carbon allocation, converting it to above ground biomass, and partitioning it out to plant functional groups, which are essential for understanding what's available for my livestock, what's available for wildlife out there in terms of forage. And so this product, we're still working through some of the details on how to process it and get it out, and it will be put into the Rangeland analysis platform as we complete it and as we publish the manuscript describing how we do this. So with that, any questions?